Hello everyone. Today our second lecture on three-dimensional geometry. In the previous lecture we have talked about the planes. Now we'll talk about the straight line. The two most important concepts of three-dimensional geometry. So first I will look into how to find out the equation of a straight line. Equation of the straight line passing through the point, any point x1, y1, z1 and having the direction vector element. You might have remember that in case of planes we talked about normal vector to the plane, but in case of straight line we'll talk about direction vector. So let's have the diagram for you. So this is a three-dimensional coordinate axis ox, oy, oz, and you have a straight line L is a straight line and A is the fixed point on the line. Let the coordinate of A be x1, y1, z1. Okay. Cartesian coordinate, and P is a variable point anywhere on the line L. So coordinate of P is suppose x, y, z. Okay. And the direction vector is B. That is the direction that gives the direction of the straight line. So B has component suppose and the direction cosines of the vector is given by element. Suppose element are the direction cosines. So the direct you can get AP from that equation from the line AP. You can calculate AP. AP is nothing but your x minus x1, right? Y minus y1, okay, and z minus z1, right? Now this AP vector and the direction vector are parallel or they can coincide. So what will be the condition? The condition is that x minus x1 by L, y minus y1 by M. So if I write x minus x1 by L equal to y minus y1 by M and z minus z1 by N, right? So this is the canonical form of the straight line passing through the point x1, y1, z1 and having direction vector or the having direction vector components element direction cosines, having direction vector whose components are element, right? So look at that. This is explained here also in the material. Since this vector is collinear with the direction vector, their coordinates must be proportional. So you have the canonical equation or symmetric form of the straight line. This is called the canonical equation or symmetric form of the straight line. Okay. Next. So what will be the vector form of the line? It's very easy. You see the position vector of A is A and position vector of P is given by R. So AP can be calculated by R minus A, right? It is R minus A. AP can be calculated in vector in terms of position vectors R minus A. Now R minus A is parallel to the direction vector B. So you know that two vectors are parallel, then one of them can be expressed as a scalar multiplication of the other. So you can write R minus A equal to lambda B. Okay, lambda is a scalar. So you have finally the equation of the straight line R equal to A plus lambda B. That means this vector form represents the straight line passing through a point whose position vector is A and whose direction vector is given by B vector, right? This is the straight line if it passes through the point A, that is whose position vector is A vector and whose direction vector is B. So it is given in the form of this. So this is the vector form of the line, right? Next, what is the equation of a straight line passing through two given points? So you have two given points. Suppose A is a point whose Cartesian coordinates are x1, y1, z1 and B is a point whose Cartesian coordinates are x2, y2, z2 and P is the point x, y, z. right? P is any variable point on the line and it is given by xyz. So we can write ab, we can write ab, okay, we can write ab as x2 minus x1, right, y2 minus y1, okay, and z2 minus z1, right? This is the vector AB, and already we have calculated in the previous that AP is x minus x1. You can calculate AP also, right? And this gives, actually AB gives you the direction. AB gives you the direction vector. This is the direction, right? So AP can be calculated as x minus x1, y minus y1, and z minus z1. These are the components. So AB and AP are uh, parallel or coincident, so their components will be proportional. Okay, so we can write that if their components are proportional, we can write x minus x1 by x2 minus x1 equal to y minus y1 by y2 minus y1 equal to z minus z1 by z2 minus y. So this is the canonical equation of the line through two given points x1 y1 z1 and x2 y2 z2. And what will be the vector form? Vector form is, yeah, this given, the position vector of A is given as A vector, position vector of B is given as B vector, and as usual the position vector of P is given as R. So you have AB can be written in terms of vector as B minus A, right? It is given as B minus A, and AP is, once again we can write R minus A, right? So these two are parallel or coincident, so we can write R minus A equal to some scalar multiplication of B minus A, that is lambda into B minus A, right? So you have R equal to A plus lambda times B minus A. Lambda is a scalar. So this is the calculation of a, this is a vector equation of a line passing through two points, passing through two given points. You look at that, this is the expression just already proved. So it's very simple. You can convert your Cartesian result to vector, or your vector result to Cartesian. If you want to convert this to Cartesian, then just replace your R by xyz, that is the Cartesian coordinates components, A by x1 y1 z1 and B by x2 y2 z2, and you will get the Cartesian form of the line. Okay, so you want to check that? Okay, let me show you. Let me show you. This is the Cartesian, this is the vector equation. How to convert the vector equation to the Cartesian form? Okay, just wait. Yeah. Okay. Okay. Yeah. This is the form. Okay. Now your R is replaced by XYZ, right? And A is replaced by X1 Y1 Z1, right? X1 Y1 Z1, and plus lambda, and this will be this is given by, this is actually okay, you can write this is lambda times B is x2 y2 z2, right? And this is minus lambda x1 y1 z1, right? So in this way you can put it into the ratio. If you calculate this one x1 y1 z1, take common 1 minus lambda, so you can write it into the symmetric form of that. Okay, no problem, you just have to replace and get the form, because it is the ratio. You look at that in the Cartesian form, it is the ratio. Yeah, this is the ratio x minus x1 x2, yeah, x minus x1 by x2 minus x1, y minus y1 by y2 minus y1, and z minus z2. Okay, sorry. Okay, yeah, so this is the form, right? This is the form. So I gave you the idea of the how to convert your vector form to Cartesian form. It's very easy. Next, yeah, this is the form. Now I will talk about parametric form. What is the parametric form? Parametric equation of the straight line passing through the point x1 y1 z1 and having the direction vector element. Okay, so you know that this is the canonical form of the line. You just write this ratio equal to R, right? R as a scalar R. So it will represent x equal to x1 plus LR, y equal to y1 plus MR, z equal to z1 plus NR. So this represents any point on the line for any value of r. If you change the values of r, it will give you different points. So r is the only parameter of the equation. So this is called parametric form. It represents any point on the line. If you need any point on the line, just replace this equation equal to r, and you will get x in terms of r, y in terms of r, z in terms of r. So that will give you the parametric form of the line, parametric equation. Now, what is a perpendicularity, condition of perpendicularity of two lines? As usual, it's very simple. If two lines are perpendicular, that means their direction vectors are perpendicular. That means if element L1, M1, N1 and L2, M2, N2 be the direction cosines of the two lines which are perpendicular, then the dot product should be 0. So that is the only condition of perpendicularity, right? So the condition of perpendicularity of two lines is given by the dot product is 0. L1, L2 plus M1, M2 plus N1, N2 equal to 0. And condition of parallelism of two lines given by the equations. That is, you have two lines, x minus x1 by L1, y minus y1 by M1, z minus z1 by N1, and so on. So you have two lines parallel. If two lines are parallel, right, then that means their direction vectors are parallel. Their direction vectors are parallel. So direction vectors are components L1, M1, N1, L2, M2, M2. Their ratios must be proportional, right? Their ratios must be proportional. Yeah. Okay. So L1 by L2, you can write L1 by L2 just like vector M1 by M2, okay, and N1 by N2, just like this. Got it? So this is the condition for parallelism. Now, what is the condition of perpendicularity of a straight line and a plane? So you have a straight line which is perpendicular to the plane, and the equation of the plane is given by ax plus by plus cz plus d equal to 0. You can see the plane. This is the plane. Okay. This is the plane, and normal vector of the plane is given by, this is the normal vector of the plane ABC, right? Its components are ABC. Normal vector has components ABC. You know that because we have the lecture video on plane also. So, and the line is given by x minus x1 by L, y minus y1 by M, z minus z1 by N. So its direction vector has components element, right? Its direction vectors are component element. Element as a direction cosines, right? Now look at that. Your direction vector alpha and the normal vector n are, right, they are parallel, so they must be collinear or parallel, right, if the straight line is perpendicular to the plane. So their ratios will be proportional, right? Okay. So the straight line will be perpendicular to the plane if and only if the direction vector of the line is collinear with the normal vector of the plane. So that will give you L by A equal to M by B equal to N by C. Okay, that is the condition of perpendicularity of a straight line and a plane. Now, next topic is condition for a straight line to lie in a plane. This is a very important thing. What is the condition for a straight line to lie in a plane? So suppose this is the plane, and the plane equation of the plane is given by ax plus by plus cz plus d equal to 0. This is the normal vector to the plane, okay, and suppose this is the line which lies on the plane, and the line passes through. You see the equation of the line is x minus x1. This is equation 1. This is equation 2, right? The equation of the plane is equation 2, and the line passes through x1, y1, z1. So naturally the first condition is that if the line lies on the plane, then x1, y1, z1 is a point on the plane. Okay. So if the line passes through the point x1, y1, z1, then the point must satisfy the equation of the plane also. So you have ax1 plus by1 plus cz1 plus d equal to 0. That is the first condition, right? This is the first condition. Okay, condition number 1. Number 2, what is the direction vector? Direction vector is this. Direction vector has component. This alpha is the direction vector, right? And has components element. The direction cosines are element. So this direction vector and the normal vector is orthogonal, that is perpendicular. So their dot product should be 0, right? Their dot product is 0, alpha dot n equal to 0. And that will give you AL plus BM plus CN equal to 0. So that is the second condition for a line to lie in a plane. Okay. So that gives you the second condition, AL plus BM plus CN equal to 0. So these two are the important conditions for a straight line to lie on a plane. Okay. These two are the important conditions. One, the plane satisfies the point which straight line passes through, and the normal vector to the plane and the direction vector of the line are orthogonal. That is, the dot product is 0. Next important thing is condition of coplanarity of two non-parallel straight lines. So if you have two non-parallel straight lines, right? If you have two non-parallel straight lines, what is the condition of coplanarity? That lies in a plane. They lies in one plane. This is suppose xy plane. So they lies in a one plane, xy plane. What is the condition of coplanarity of two non-parallel straight lines? So suppose the first line is given by x minus x1 by L1, y minus y1 by M1 equal to z minus z1 by N1. So the first line passes through x1, y1, z1 and having direction vector alpha, and alpha is having some direction cosines L1, M1, N1. Second line passes through x2, y2, z2 and its direction vector having components L2, M2, N2. These are the direction cosines. So these are the first two lines. And let the equation of the plane be ax plus by plus cz plus d equal to 0 as usual. So normal vector is ABC. Okay. Now, already we have learned what are the conditions for a line to lie on a plane. These two, right? So I will apply this is here. So if the first line lies on the plane 3, if the first line, then you have these two equations, equation 4 and equation 5. That is the point x1, y1, z1 satisfies the equation of the plane, and the dot product of L1, M1, N1 and A, B, C are 0, right? So these two are the conditions. And similarly, the second line lies on the plane, then you have the second point, that is x2, y2, z2 satisfies the equation of the plane, and the dot product of the direction vector and the normal vector will be 0. So you have equation 6 and equation 7, right? Okay. So subtracting 6 from 4, what is your 6? 6 is ax2 by2 cz2 plus d, and 4 is ax1 by1 plus cz1 plus d. So if you subtract cx 6 and 4, d will be eliminated. So you have a relation between ABC. ABC equals, that is equation 8. Now eliminate ABC from 8, 5 and 7. That is AL1 plus BY M1 C. This actually 5 involves ABC, and 6, 7 also involves ABC, and 8 is also involving ABC. So you eliminate ABC from 8, 5 and 7, we get this x1 minus x2, y1 minus y2, first row z1 minus z2 and L1 M1 N1, L2 M2 N2. This is the 3 cross 3, the third order determinant, and this determinant equal to 0. So this is the condition of coplanarity of two non-parallel straight lines. If two lines are coplanar, if two non-parallel lines are coplanar, then this is the condition of coplanarity. Okay. So it's very simple. You check the determinant whether it is 0. If it is 0, then the lines are coplanar. If it is not equal to 0, then the lines are non-coplanar. They are not coplanar. Okay. Now, next is, what is the equation of the plane containing two intersecting lines? That means if two non-parallel lines, they must intersect. When they intersect, if they lies on a plane, otherwise they can't intersect. Suppose if I draw a three-dimensional axis, Cartesian axis, so this is your xy plane, right? And this is your yz plane. So if I consider two lines, one is the yz plane and another in the xy plane, they will not intersect because they lies in the different planes, and these lines are called skew lines. If they lies in a different plane, they will never intersect. So only they will intersect if they lies in a plane, right? In one plane. So equation of the plane containing two intersecting lines so the equation of the plane passing through the first line, that is the first point x1 y1 z1, is given by equation 1. a into x minus x1 plus b into y minus y1 plus c into z minus z1. And since these two lines are lies on a plane, so you have the conditions, these two conditions, al1 plus b1 m1 plus c1 n1 equal to 0. Similarly, the second condition. So eliminating abc, you will have x minus x1 y minus y1, this determinant, third order determinant. So you look at that, you have a variable here xyz, and this represents a first order equation in xyz. You know that first order, any first order first degree equation represents a plane. So this represents a plane containing two lines. You can write the plane in this form also, taking the second point, x minus x2, y minus y2, z minus z2, right? And L1, M1, N1, right? And L2, M2, N2. Okay? So you may follow this also. Okay? So this is the equation of the line. Either this or equation of the plane containing the lines. Equation of the plane containing the lines. Either this or this. Okay? Next. Now I will talk about distance of a point P from a straight line AQ. So P is a point and AQ is a line. So here distance of a point P is a point x1, y1, z1. Okay. So P is a point, any point x1, y1, z1. And equation of the straight line AQ is given by x minus alpha by L equal to y minus m by y minus beta, sorry, y minus beta by m, this is alpha, and z minus gamma by n. Okay, and this point A is actually alpha beta gamma. I'm supposing that alpha beta gamma. So the equation of the line is given by this, sorry, L. This is L. This is not alpha, sorry, I made a mistake here. Lmn. Lmn is the direction. This is the direction vector. Direction vector is given by whose components are given by Lmn. Direction cosines actually. Okay. Now draw PQ perpendicular to the line. So this is perpendicular 90 degree. Okay. Now you can calculate AP. What is your AP? AP squared. You can calculate AP squared. AP squared is x1 minus alpha whole squared plus y1 minus beta whole squared and plus z1 minus gamma whole squared, right? This is the distance between 2 points. Okay. Now if I apply the Pythagoras, AP squared is equal to PQ squared plus AQ. Actually AQ, you look at that, AQ is the projection of AP in the direction of AQ. AP is the projection of AQ is the projection of AP in the direction of AQ. So if I write then what is the projection AP? What is the projection AQ? AQ is given by, you see its component as x1 minus alpha into L. So AP vector is given by, actually AP vector is given by x1 minus alpha, y1 minus beta, z1 minus gamma. And Lmn is the direction vector of AQ. So its projection in that direction will be dot product of AP with this direction vector. So x1 minus alpha, right, dot L plus y1 minus beta dot m, okay, plus z1 minus gamma dot n. This is the projection. This is the projection, okay. This is the projection AQ. AQ is actually the projection of AP in the direction of Lmn, in the direction of alpha, your direction of the vector, which components are Lmn. So this is the projection, okay. Now you have AP already calculated. This is your AP. AQ is the projection, AQ square, and you will get PQ square, the distance of the point P from the line. So PQ square can be calculated by, PQ square is x minus alpha whole square. This is the PQ square, and this is actually a projection. This is projection square. So if you simplify this using the Lagrange's identity, it will be written in this form, this determinant form. First determinant, you look at that, Lm. Next determinant, Mn. and the last one NL. So in the first determinant, your N is missing. In the second one, L is missing, and the last one, M is missing. So you can remember this by this determinant also. This represents the, if you calculate it, this will give you the distance formula. This is actually Lagrange's identity. Actually, this is the form. Or you can remember this also, the proof also, for your better understanding. Okay. Now I will go to the most important thing of your straight line, that is uh, shortest distance between two skew lines. Already I talked about what is a skew line. Skew lines means these two lines are different planes. They are not in the same plane. So if you draw the axis, this is your, yeah, this is your x, this is your y, and this is your z. So the first line in the yz plane, L1 in the yz plane, and L2 in the xz plane. So these two lines are skew lines, and you have to find out the shortest distance between two lines. Okay. Now, shortest distance is the line, is the distance which is perpendicular to both the lines. That is the first point. Okay. Now, these two are the lines, x minus x1 by L1. So, the first line is given by L1 is given by x minus x1 by L, y minus y1 by M1, z minus z1 by N1. And the second line is passes through x2, y2, z2, and L2, N2 is are the components of the direction vector, right? This is your first line, L1, and this is your second line, L2. Okay. Now, let element be the direction, element be the direction cosines of the vector that lies on the line of shortest distance. So this is a line actually. So along the line, you assume a vector or a line whose direction vectors are components, whose direction vector has components element with the direction cosine of the standard shortest distance line. Okay. So if this is perpendicular to both, so this is having component element, this is the direction vector, component of the direction vector of the first line, and this is the component of the second, right? And along the line of shortest distance D, you are taking, along this direction, you are taking the components element. So naturally, they are dot product. These are perpendicular, orthogonal to both the lines. This line. So you have L1, M1, and N1 equal to 0, and L2 plus their dot product. It should be 0. So if their dot product is 0, you have these two equations, right? You have these two equations if they're perpendicular to both the lines. Okay. Now suppose this is the point A here, and this point is given by x1, y1, z1, and this is the point, suppose B, this point is given by x2, y2, z2, right? And these 2 points are suppose A dashed and B dashed. Now look at that. A dashed, B dashed is the projection of the line AB. A dash, B dash, you look at that, you just try to imagine. This is a three-dimensional abstract concept is required. Actually, A dash, B dash is the projection, or A dash, B dash, or A prime, B prime is the projection. A prime, B prime is the projection of AB. Right? This is the very important concept in shortest distance. Projection of AB actually. So how will you calculate that? Okay. So before that you can calculate element by solving these two equations. By solving these two equations, you can calculate element by cross multiplication method, and you can write this equal to root over L square plus M square plus N square. And you know this is element are the direction cosine, so this will be 1. So you have 1 in the numerator, and finally you have L, M, N in terms of these known quantities. M1, N1, N2, L2, M1, everything is known to you. So you got element in terms of these known quantities. Okay. Now I was talking about A dash, B dash be the respective points of projections of A and B on the straight line. Then standard shortest distance is actually A dash, B dash. Therefore, shortest distance is nothing but your A dash, B dash, right? and that is the projection of AB on the shortest distance line. And how will you calculate the projection? Already calculated. Yeah, go to the diagram. Yeah, projection of A dash B dash on AB, projection of AB on A prime B prime is actually this AB can be written as x2 minus x1, y2 minus y1, z2 minus z1. Okay, clear? The AB vector is given by x2 minus x1, y2 minus y1, and z2 minus z1. And if it is the projection in the direction of the shortest distance, then the dot product of with element will be 0. So you have x2 minus x1 dot L, because AB is the AB, A prime B prime is the projection of AB in the direction of the shortest distance. So you have x2 minus x1 dot L, y2 minus y1, right? Y2 minus y1 dot M, and z2 minus z1 dot N. That is the projection. Okay. That is the projection. That will give you the projection in that direction. That is how to calculate projection. Already we discussed projection also here also. You look at that, you have a projection concept. Already I gave you the projection. So that will give you the projection in that direction. And dot product 0 in that case, where you have L1, because element is with the shortest distance is perpendicular to both the lines. So you have dot product 0 in that case, not in the projection. So now this is the projection of this, and this element, you just replace your element here, you will get this type of expression. So this will give you the shortest distance in Cartesian form. Okay, but its vector form is very simple. So you have two lines just like this. This is the direction vector p1, and you have a direction vector of the second line b2. Skew lines, both are not in the same plane. Okay, and this is suppose your a1 point, the position vector of the point, and this is suppose a2 point, right? And this is the shortest distance. Okay, this is the shortest distance, and shortest distance is perpendicular to both the lines. Okay, so shortest distance is the projection of these 2 points, this line AB. Shortest distance is actually the projection of AB along that direction. So you have, and b1 cross b2 is actually the vector along the shortest distance. B1 cross B2. If you take the cross product, that will be perpendicular to both the vectors, and that will be along the shortest distance. Okay, so you will get this type of expression, similar expression as the Cartesian form. Okay, so this is in the vector form also. Okay, and lastly, if you want to find the equation of the line of shortest distance, if you want to find that this is the shortest distance, if you take the modulus of this and if you calculate this, this will give you the distance. Now if you want to find the equation of the line of shortest distance, so you need equation of the plane through first line, and the shortest distance line is given by this, right? This determinant, already you have learned how to write this. And if you want to write the equation of the plane through second line and the shortest distance line, that will be given by this. Okay, now these two line will combine, these two plane, equation of the plane, these two plane will give you the line of intersection. You know that two planes gives you the line of intersection. Okay, so this shortest distance line is the line of intersection of these planes, and this is given by this equal, this both of them equal to 0. So both of them will give you the line of intersection. That will give you the line of shortest distance. Lastly, what will be the angle between two lines? It's very easy. If you have the direction vector a1, a2, if you have two planes, oh, intersecting lines, yes. So you have two intersecting lines, means these two are planes. Plane will intersect in a line. If you want to find out the angle between them, that means the angle between the normal vectors. So this is the formula for the normal angle between the normal vectors. Always remember, two planes intersect in a line. So if two equation of two planes are given in the problem or any theoretical part, that means they will give you the lines. They will produce the line. Okay, so they will give you generate the lines by intersecting, because if you take two planes, intersecting planes, they will generate a intersecting line, the line of intersection of two planes. That is why the language is. Okay, so I hope this video will be helpful to you. So subscribe my channel, put some comments on in my video, and see my next videos also. Thank you all of you.